A magic square is a square of cells with numbers where adding all the cells in a row, column, or diagonal give the same number. An infinite number of magic squares can be found, but not if the numbers are square, without making some numbers the same. I've attempted this problem about a year ago, and since trying again, I learned some new tricks that could be useful outside this problem, and that's why I'm making this video. Firstly, I'm going to show all the restrictions of what these 9 values must be by doing sums along each of the 8 directions. So these are all of the equalities with a to the n, and since they all have a to the n, it can be cancelled out. And I do the same process for the rest of the variables. Here are just a few of those equations. We can do substitutions for 5 of these variables to reduce our 9 variable problem to a 4 variable one. There's one other reduction we can make. We know the sum along a row and a diagonal must be the same, and you can see these two are different. This means we can make one more reduction. Now every sum along any direction gives the same value. And since all variables here are to the n power, you can use this same form for square numbers, cubic numbers, and so on. But we're just interested for when n equals 2. Now in the first video I made, I put in a lot of work to find these 9 very nice relations to the right, where if all these are true, then you found a solution. But in the last video, I made some unnecessary assumptions about what each variable should be, but this time I didn't. Fortunately, it turns out if you plug in the equations on the left to the ones I found on the last video on the right, they're all true. So this means I can use my previous work. So, what did I find out? Well, these are the Diophantine solutions for each of the equations, where you can put in any PQ value for each line, and it will conform to the equation on the left. The problem is, there are multiple definitions for each variable here, so you get this mess of equations you have to solve first, and this is where I get stuck. This E equation is particularly nasty, so I start here. One idea I try is to assume I find some C value for each expression separately, and then try to make them all equal later. Notice I'm using C as a square value, which will be important later. This is just the Pythagorean theorem, and there's a known Diophantine solution, which I show here. Now I'm going to try to make every equation equal to C1, C2, C3, C4 squared. Now, here's the trick and why I use C squared values. The C values can go inside the parentheses of each term, and this is how I can still keep that a squared plus b squared equals c squared form. This lets us get a set of solutions for P1 through P4 and Q1 through Q4, shown below. Great, let's try and solve this D equation next, using the same trick. This one's more difficult to solve, and there isn't a known Diophantine solution. Can we make one? In the previous video, I showed you can solve circle equations generally, but what about this conic? What was the process? I'll give credit here again, but the idea is if you have some circle equation, and if you can find a rational point on the circle, you can then draw a slope that is also rational through that point. And then any other point that rational slope intersects with will give you another rational point. From the rational solutions, you can then derive the integer solutions. But does this work with conics other than the circle? Can you solve the general conic equation like this? Let's find out. First, assume a solution was found for some x and y with x0 and y0. Here's the slope equation that then passes through that conic. Perform substitutions and try and solve for x. Here is a huge time save I learned while doing these problems. So this is the quadratic formula, but notice I'm setting x0 to that instead of x. I already assumed earlier we found some solution x equals x0. Now what I'm going to do is skip calculating b squared and 4ac by solving for the discriminant instead of for x. All of the terms on the right are terms we know, so this root of the discriminant has been found very quickly. Now I can solve for x. There are 2 solutions, and the positive root discriminant will give us back x0, so I only care about the negative root discriminant. Now I can find y by substituting x into the slope equation. Remember, we want integer-only solutions, so this is how we do it. I will multiply the entire equation by the denominator squared, which I'm calling z. And remember that the slope m is rational, so I can set that to p over q. So notice that multiplying almost works. Look at the very top equation now. If I was dealing with the circle equation, I wouldn't have those d, e, and f terms, and the denominators would all cancel out perfectly. But since I have the single variable terms up there, there is a leftover denominator, z, and the f constant kept the whole denominator squared quantity. Fortunately, I can still multiply everything by q to the 4th, and x, y, and z no longer have any fractional terms. But those z's weren't part of our original equation we were trying to solve. The only way to make it be our original equation is if the value of z is 1. So that's an extra condition we have if we have those d, e, and f terms. Going back to our original problem, we can now solve this. Here's the general conic, and I'm going to set d and e to 0 and f to 1. Notice how the z squared in the general conic perfectly matches the z squared in the equation we want to solve. Because of this, we can use the general conic formula we just made. Here's the solution, and now it's time to plug it into the d equation. Z here isn't that important, it's just what the value of x squared plus 2xy minus y squared will be. P1 and Q1 now have two values they could be. The E equation earlier told us what P1 and Q1 should be, and now this equation tells us a different thing. So they must be the same. If I multiply the equation we just found by C2, C3, C4 squared, they are nearly the same. The only nice way to make this work out is if the values inside the parentheses equal each other, which is what these two equations are. Don't worry if this is confusing, it will not matter later anyway. With the double values of P1 and Q1 resolved, here's what P7, Q7, P6, and Q6 look like. Time to do the same trick where we make everything equal to C'1, C7, C6 squared. C'1 is for this P1, Q1 equation because we already signed the value of C1 to the previous P1 and Q1 equation. Again, sorry for the confusion, there's just way too many terms to deal with already. This is what the final form looks like, and there is one more problem with this. We just modified what P1 and Q1 must be for this equation to work by multiplying extra terms to it. This changes what our previous solutions were for P1 through P4 and Q1 through Q4. Therefore, all of those previous terms must be recalculated by being multiplied by the same values. This is getting messy really quickly, but it's working so far. What if we keep going? Here's the B equation, and notice the P2, Q2, and P7, Q7, which we already have values for. I'm just going to focus on P7 and Q7. We'll end up with new equations for them, and just like last time, we'll have to make sure all the P7s are equal and all the Q7s are equal. This requires us to set the quantities inside those parentheses equal to each other, and thus we get these two equations. Notice how similar these forms are this time. In fact, if you swap the A and alpha variables together, and the B and beta variables together for one equation, you'll end up with the other equation. Is there even a set of values where this is possible? One side has all negative terms and the other side all positive terms, so it seems unlikely. Can we prove there's no solution? Here's the two equations on their own. All I did was change the variable names. Look at the first equation and notice that 2c squared plus 2cd is even. Therefore, minus 5a squared minus 4ab minus b squared is even. From there, we can conclude that either a and b must both be odd or both even for the right side to be even. But remember that a and b and c and d must be swappable, so if a and b is a certain way, then so must c and d. Basically, we end up with two choices. Either a, b, c, and d are all odd, or they are all even. If all of them are even, then the values of the variables are reducible. This is because every term in those equations have two variables multiplied together. And so if they're all even, we know we can divide every variable by 2 and still get a solution, and keep dividing by 2 until we get a solution set where all of them are odd. The only exception is if all of the variables are 0. So we just need to worry about the odd case. I'm modifying a and b to force them to be odd numbers here, and this is what happens. Notice all the terms on the left are even except for the negative 5. Evens plus evens give more evens, but an even and an odd give an odd. And notice the right side is even because c and d must be odd, and an odd give an even. Therefore, there is no solution here except for when all the variables are 0. And if they're all 0, we will end up not with unique solutions to our magic square of squares. So is that it? Did I prove there's no solution and finally solve this unsolved problem? Not quite, because I made an assumption about what the values of these equations must be. All I really did prove is that they cannot all be square values. As a short aside, you can get a much quicker resolution using this process for the case of the semi-magic square of cubes. A semi-magic square is like a magic square, but you do not need to have the diagonals sum to the same value, so that's 2 fewer requirements. These are the equations that need to be satisfied, just 2 sets of double equalities. Let's try the same trick of finding c values for each and then setting them all equal later. Instead of making c a square, we would need them to be cubes. Well, if you take a short look at what we just constructed, it's the same thing as x cubed plus y cubed equals z cubed. Using Fermat's last theorem, there are no solutions to this. Okay, is there another way to solve this that doesn't require restricting the values to be squares? There is an identity that looks similar to what we have here, but it only works with two sums of two squares, not four sums like we have. I then tried to figure out if this could be extended somehow to work for four squares. I would need twice the variables for my solution, so one thing I tried was adding four more variables. Instead of just having a, b, c, and d, now there's e, f, g, and h. What if I then apply this identity twice, one for a, b, c, and d, and one for e, f, g, and h separately? It would look like this. The identity gives us two equations equal to each other. This is where the moment of genius happened, because if you took a large step back and squinted at this form, it looks like the entire expression also matches the form of this identity. I put in a prime through d prime values where the parentheses are to help show that easier. But it's two quantities squared and summed, multiplied by another two quantities squared and summed. So yes, you can use the identity again. And since we got two equations that equaled each other when we used the identity once, we can use the identity on each of the two equations to get two more equations each for a total of four. This is now a set of four pairs of squares summed, all equal to each other. We found our solution. Before I move on, there is a problem that shows up when finding further solutions. Every time we find a solution set like this, when we substitute those values into other equations, we tend to end up with equations with higher powers than quadratics, which we can't solve. So, for example, here's the A equations. We now have P3 and Q3 defined, but notice that every term in there is four variables multiplied together, which essentially makes it a quartic. And notice how we have two of those terms multiplied together in the A equation, so we would end up needing to solve an octic equation? Is that even the right word? I don't know. Another issue is things like the D equation, where there are three values all equal to each other, which we also don't know how to solve generally. Okay, so can we avoid solving higher order equations as long as possible? That's what I try next. But if we're going to avoid solving quartics and such, we will need even more powerful quadratic solving methods than what we did for the general conic. We will need to solve equations with more than two variables. Now the next question, is this possible? Can we solve this equation, for example? Let's do the same process like what we did with the conic. Assume we found an initial solution, and then try draw a rational slope line through the equation. What even is the equation for a line in more than two dimensions? The form looks like this, and here I'm just showing that this is in fact the same line equation that we've been using. Okay, so for four variables, this is what that line looks like, and the line is going across four dimensions in this case. The idea then is to get everything in terms of x first, so that we can solve for x, just like before. Here I'm using the same trick, where I avoid solving for the discriminant by setting x to x0. Now that x is solved, I have w, y, and z equations that I can substitute x into. In this case, multiplying everything by that denominator squared causes it to go away completely. Now I multiply by b to the fourth, and this is our integer set of solutions. So this does work in higher dimensions. Let's check that this does what we expect. Here's a Pythagorean quadruple. It's like a Pythagorean triple, but with three terms summed to a square instead of two. The solution for this is known, but what if we use our formula instead? They look a little different, but both equations are true when plugged back into the top equation. But this still won't be enough. Now that I know this works in higher dimensions, I want even more power. I want to use even more terms. In fact, an arbitrary number of terms. And I want it to work with constants and single power terms, like when I solved the general conic. This is where I kind of go crazy and try and find out if I can find a formula for this, which I now call the infinite term quadratic Diophantine formula. To even have a chance with this, I need a smarter system than what I've been using. Here's a sort of matrix where the first row and column are labels showing what terms I want multiplied into the cells. So for example, the cell with the C5 term will be multiplied by x1 and x2. For the C1 term, it will be multiplied by 1 and 1, so it's the constant. Also notice how I'm ordering the coefficients. It's ordered in such a way so that if I expand this matrix to include more x terms, the order of the existing c values will not change. So when I write a table like this, that correlates to wanting to solve this equation. In this case, I'm just solving the general conic equation again, so this should look familiar. All the x values are variables I want solved, and the initial conditions will now be defined in terms of y's, where yn is a solution when plugging it into xn. One more change, the line equation will be written in this form from now on, and instead of p's and q's or a's and b's and c's, it will all be written in terms of vn. The v variables will now be the free variables that you can plug into to get any solution. Here I'm multiplying the original equation by v1 squared first. This is just so substitution gets a little simpler, so I'm not dragging around fractions everywhere. Here's another smart thing I'm going to do. I'm going to solve the quadratic equation like before, but not define a, b, or c. It turns out I don't need to substitute in a, b, or c, in this case c at all, until I already know what the solution of my x's are going to look like. I'm always going to find x1 first with this process, and all other x terms I can then solve once I find x1 by using the appropriate slope equation. Here I'm getting rid of the denominator a value by multiplying my original equation by a squared. Just like with the conic, this will leave values of a in non-quadratic terms. Now I can substitute in the a and b values. Notice that c doesn't appear here. It never has to be computed. This is our solution for the conic, just with different variables defined. Now to go one step further, I'm going to introduce a third x variable into this matrix and then solve the resulting equation. Is matrix the right word? It's more like a table. Whatever. Notice that each slope equation looks very similar. In fact, you can get a general slope equation from this for any xn. Now that I know I don't need to compute c, I don't even show it here in this expanded form. And it is still a massive equation. Just like with the slope, the solutions for x can be generalized into the form below. It even works with x1, despite it looking so differently. Computing this took a long time, and I left out a lot of intermediary work for your sanity. I cannot do another step like this. At this point I try to look for patterns, using the previous two solutions I found, to look for further solutions. So I want to solve this one. Can I extrapolate what the solutions will be based on the previous solutions instead of doing the work? Firstly, the a value, the denominator. It looks like the pattern is only terms of power 2 are included, and xn is replaced with vn. So that's what I do for the next a value. Here's the full equation I'm trying to solve again for reference, and I'm going to replace xn with yn for clarity reasons. I'm looking at one of these v terms at a time. Here's the v1 squared term belonging to the x1 equation. So looking at the terms inside the parentheses, it seems like all of the terms with y1 are included in that equation, but one y1 is removed from each term, and the sign is flipped. Okay, what about the next term, v1, v2 belonging to the x1 equation? Here it looks like all of the y2 terms are included, except for the y1, y2 term, which would be c5. Additionally, the c6, y2 squared term has a 2 coefficient inside the term in the solution. So the general rule seems to be for any vn, vz term belonging to the equation xn, where those n's match, that non-matching term, the vz term, all of those yz terms are included in those parentheses, except for vn, vz. And in the special case, where one of those terms is a square, that term will have a 2 coefficient in front of it. And of course all of those terms are negated, and a yz is removed from each term. Okay, what about that last term in the first x1 equation, c6y1, belonging to the term v2 squared? Well, in this case, none of those subscripts match x1. They're all 2's. So it seems if you have some VA, VB term where A and B are the subscripts and neither of them match the subscript of the x equation it belongs to, then you just need to find the YA, YB term. So in this case it'd be C6Y2 squared. But instead of including that Y2 value, it's the YN value, where n is xn, the equation that it belongs to. That's incredibly complex and confusing, but I've written the 3 rules below everything, so convince yourself that you can apply these 3 rules for each of those v terms, and that the values that you get out of those rules match what's shown on the screen. Now to apply the rules to get our solutions for x1, x2, and x3, now including the x4 term. Notice how none of the original c values changed their positions inside the solutions. We didn't need to change any of the original terms in our solution, just add new terms to it. So that's it, that's the pattern. We can in theory solve any quadratic solution by using this method. Let's test it out. We need an initial solution first, so y1 to x1 equals 2, y2 to x2 equals 1, that works. And since we have single terms and constants here, we need to worry about the a value equaling 1, as ITQDF gives us a modified equation with those a terms in it. Now if we try to use ITQDF on this equation, we will end up with another a value that is the exact same as this one, so we can't just apply it again. Thankfully, this equation is pretty simple to solve. It can be rewritten into this form, and there are only 4 integer-only solutions to this. So now we convert those xy values to the v1 and v2 values, and then convert those into the x1 and x2 values. So here's what we learned, that ITQDF does have a major downside. It can give us solutions to these quadratic Diophantine equations, but it doesn't get all of them. In this case, we got just 2 solutions, but it misses some other solutions, such as x1 equals 2 and x2 equals 2. Okay, that's a bit annoying, but we could get more solutions out of this. We found 2 solutions for x1 and x2. What happens if we use those as the new initial solutions and apply ITQDF again? Here we get another form for x1 and x2. Notice that a remains the same, and so it has the same v1 and v2 solutions. A will not change depending on what we input for the y values. So here we get 2 more solutions that we can try. Let's try y1 and y2 equals 10, 9. Here we end up with solutions we already know. Okay, what about 16, 9? Okay, same deal. What about 2, 1? Okay, so in this case we just end up with a set of solutions where even if you plug in another element from that set into ITQDF, you'll just get back solutions from the same set. What happens if we put in a solution that's outside of that set? So here 4, 5 is another solution. So putting that in gets us a different set of solutions, 4, 5, and 14 and 5. And it turns out those are the only 2 you can get. So it seems in this restricted case where you have to worry about a equaling 1, you get this weird sort of sets of solutions that can only be found within each other. Now, I was running out of time here. I wanted this video to be published by deadline, so I haven't figured out why this happens or if this will always happen. If it only happens with a equaling 1 being the restriction. So I think this could be an interesting topic to explore in the future. So what about a case if we don't need to worry about the a equals 1 restriction? Well, we just need an equation without single terms or constants. Here's an example, and here's me showing all the solutions I can find through brute force. Let's say I only know one of those solutions, 1, 2, and plug that into ITQDF. Now obviously this gives an infinite number of solutions. I'm only putting some of them here, but notice how, again, it skips some solutions that were present when I brute forced it. If I pick one of those x1 and x2 values and put it back into ITQDF, I get a different infinite set of solutions, and again, it skips some other solutions in between. Now I wanted to take this to the extreme, to truly show the power of ITQDF. So here's a 5x5 magic square, reduced to a form where all the sums across a row, column, and diagonal equal the same value. I did a similar process to find this as the one in the beginning of the video for the 3x3, but I'm not showing my work here because that's not the point of this. The point is, I'm going to find a solution for the t squared cell, which has an absolutely insane number of terms in it. I first get all terms on one side so that I have n equals 0 at the other side, and then I find an initial solution. In this case, a equals 1, k equals 1, and everything else is 0. And here's the solution set. So what did we do? This makes it so that I always get a square value inside that t squared cell. In the original equation, that was all equal to t squared, where I needed to find the value of t. And since I solved for t here, I already know what the value is going to be. But good luck getting farther than this, because you will have to substitute these values that we know now into some other equations, and it's going to end up giving us a quartic equation, which we can't solve generally. Oh yeah, that was the whole point of going through this tangent. I was trying to get as far as I can in solving the magic square of squares problem, and I said I would need a more powerful process to solve some crazier equations. So here's basically the best attempt I had. I tried many other times, of course, and what I did is ignore these p and q equations that I worked so hard to find in the first video. I'm going to try something different instead. Here's the original 8 relations to solve. Notice how the first 4 equations all equal to the same value. I can therefore use the 4 square sum identity I found earlier for this. The only downside is this solution won't restrict the values to be 2e squared, but that's fine. Now remember, if I try and substitute these solutions into one of the 4 remaining equations to solve, I would end up with an octic. How can I defer solving these octics? The answer is substitutions. I'm going to redefine these 8 r values in terms of s's, so I can get all the r's in terms of s's. And notice here, I'm defining 2 r's for each s, so I'm actually going to reduce this quartic equation for each of these values into a quadratic. However, this is not enough. I'll still end up with a quartic equation to solve. I therefore need to make yet another substitution, replacing all the s's with values of t. If I tried putting these values into the 4 remaining equations to solve, I'll end up with these 4 forms, which are still quartics, but I can make one last substitution to eventually get everything into a quadratic. And that means converting all of the t values into another set of variables, in this case u's. Now this is solvable for ITQDF. Additionally, I'm going to solve the first and third equations because notice that they don't share any u terms with each other, which means I can solve each of them independently. And this is what I get for each u value. Every u value is now defined except for u9, u10, u15, and u16. Now I'm going to try and solve the second and fourth equations, and I'm going to split it up so that the terms on the left are terms that I have solved using the first and third equations, and the terms on the right are the terms that I don't have defined yet. This is where the u values need to be substituted in, which makes this a quartic equation, and so I will have to resort to brute force to find values I want for the left side for each equation. The only restriction is that the value on the left must be sum squared multiplied by 2 because of how the right-hand side is. Here is a set of u values that works. This leaves me with 2 remaining equations where u9, u10, u15, and u16 have infinite solutions. Great, so every u value is defined, and u10 and u16 happen to be free variables. But this is the easy part, because now that we found all the u values, we have to use this reverse substitution process where we need to find all the t values because they're defined in terms of u, and after we do that, all the s values, which are defined in terms of t, and finally all the r values, which we define in terms of s. So this is what happens when plugging in our u values. Let's try and solve one of the t's, t1. Notice that t1 is sprinkled in multiple of these equations we defined, so it has to equal multiple values. This is what those would look like. Notice the 13 over t8 and 11 over t3. 11 and 13 are both primes, and we want integer solutions, so t8 could only be plus or minus 13 or plus or minus 1, and t3 could only be plus or minus 11 or plus or minus 1. And for t1 to equal both of these, we have no choice but to set t equals to plus or minus 1. So each of those t's in the denominator needs to match its numerator. Okay, that's pretty restrictive, but we found t1, so let's do another one. t8 was already defined to be plus or minus 13, and we can immediately see a problem here. There are no values for t2 or t6 or t5 that we can put in to make it equal plus or minus 13. So we are just stuck here, and there is no solution for T8. Now we could try again and just input another set of U values, but again, these are quartic solutions. I had to brute force to even find a solution because I cannot generally solve it. So we're just stuck brute forcing U values until we somehow magically get a set of values that also works for all these T equations. And then there's still the problem of finding all the S equations and then all the R equations. So realistically, this is not going to happen. Okay, well, if we stopped at defining the S equations in terms of the R values, we could make this set of equations where we do use the P1 and Q1 solutions for F, H, and A and set them equal to each other like this. Notice how they're all equal to 0. We could set all these equal to each other because they all have the same terms, but this gives us a double equality set of equations to solve. And there is a set of S values and P and Q values that work for all three of these equations. This is an example. The problem is ITQDF needs to accept just one equation with one set of solutions to pass through, and the solutions that it generates actually will only work for that one equation. If you try using it for the other two equations, it will not work out. There's no way to use ITQDF to solve these double equalities, right? Let's revisit these two equations. They're a double equality, but what if we split up the equations? The general form would look like this, and this works with any pair of the expressions you use up there. Here I related P1, Q1, and P7, Q7 together, but you can use the slightly different form of the P2 and Q2 equation for this. In fact, if you swapped P2 and Q2, it's the exact same form. Let's try solving this simpler equation. Here's one initial solution I'll use. Now let's try something. What happens if I find another solution where I keep y1 and y2 the same, but find a different y3 and y4? Here's that set of solutions. Notice how x1 and x2 are not the same as the previous x1 and x2, but they look similar. In fact, they would be the same, but only if I set v3 to 0 and v4 to 0. So let's do that. Also, I kind of lied there. You can also set v1 to 0 and v2 to 0, and you'll get the x1s and x2s looking the same, but I'm just going to set v3 and v4 to 0 for this. So look at what we have here now. x1 and x2 in both cases are the exact same. What does this mean? It means either x3 and x4 from either of those solutions can be swapped with each other, and we will still have a valid solution. This sounds like the double equality we were looking for. You'll see in the moment this is in fact the case. I'm going to set P8 to x1 and Q8 to x2. P2 and Q2 have this different form, but like I said earlier, you can just swap the roles of P and Q. So I'll make P2 be x4 and Q2 be x3. Lastly, I'll set P7 to the other x4 and Q7 to the other x3. This is a valid solution. We can in fact use ITQDF to solve these double equalities. The only downside is we have to drop two of those v values, which effectively reduces our solution space. The same process will now be used for the second double equality. Notice that P7 and Q7 are defined in both equations, so we'll have two different forms for them, so we'll have to make sure they're equal before continuing. Now I was trying to find some v values that you could put in as an initial solution, but I couldn't find anything except for all zeros, so what's going on here? It becomes a bit clearer what's happening if we treat this as a system of equations. I'm multiplying the first equation by 9 and the second equation by -4, then summing the two equations together. We end up with this reduced form, which is easier to solve, and it turns out there's only one integer-only solution to this, 0, 0. So that's why we couldn't find any solutions earlier. We can find one, we just need a different initial solution to pass to ITQDF. Here I'm going to try something different. I'm substituting in P7 and Q7 to the second equation, and brute force solving it as a quartic. Here's a solution, v1 equals 2 and v2 equals 3. Now here's what happens. That quantity equals 55,982. So I just need to find two other values that you can put into P7 and Q7 to get that same value, and then I can put those in for P1 Q1 and P6 Q6. There are a few options, so I'll just pick two of them. And that's both of those upper equations fully solved. Now, of course, there's a problem with this, because there always is. Those are 2 out of the 4 double equalities we needed to solve. Here are the other 2, and notice that it has terms that we already defined, the 1s, the 8s, the 2s, and the 6s. So we put those values in, and we end up with an impossible equation. So the solution that we found is not valid. There is another option, and that is to withhold solving the quartics for P7Q7, P2Q2, and P8Q8. And this is what that would look like, with all 4 double equalities included. And even with ignoring the P6Q6s, the P5s, and Q5s, I was just trying to find a solution for P1Q1, B1V2, and I couldn't find solutions. I did this huge exhaustive search. I was even just searching for ratios of P1Q1 and B1V2, because that is faster. And even with trying to find equivalent ratios, I couldn't find anything. So this is where I had to stop. I'm out of time and patience and ideas. But in the process of trying to solve this problem, I learned a lot of new tricks, and my hope is that with this video out, now other people can benefit from the work that I put in. One last thing I want to share, I made a web service for ITQDF. So you don't even have to do all the work that I showed in the video. You can just put in the equation you want to solve with your initial solution, and it will just do all the heavy work for you. So let's say, for example, I wanted to solve a 4-variable Diophantine. I would set this number input to 4, and then here's that table that I showed in the video. So you just set in the coefficients that you want. So I want to solve x1 squared plus x2 squared plus x3 squared minus x4 squared equals 0. And then it will show your equation you're trying to solve here. You can just double check that. And then here I want y1 equals 1 and y4 equals 1. So this is 1, 0, 0, 1 for x1, x2, x3, x4. You just need to confirm that those y values will equal 0 if you plug them into the x's here. So once you do that, you just click on this button, and it will spit your solutions out for you. So here's all the x values, and here is the a value in case that's needed, in case you have single terms or constants. And the domain is up here, but I'll also put a link in the description.